Hello again. So in this session, we want to see how we can represent the stresses in a fluid at rest and also at motion. So let's see how we can describe and what do these stresses actually refer to when we have a fluid that is moving and also a fluid that is at rest. Okay. So when a fluid is at rest, meaning that it's not moving, it's kind of steady, it's not there. For example, you can imagine you have a dam, the flow is just there, or you have a tank of water and the flow is not moving. In such fluids, in a fluid at rest, in such a fluid, the forces or the stresses are at equilibrium, right? So in a fluid at rest or in a fluid that is in equilibrium of the forces, because we don't have any motion, right? So the sigma F based on Newton's formula, sigma F, which equals ma, because we don't have any motion, this should be 0. So there is an equilibrium of the forces. There is no force that is kind of dominant and it's not kind of accelerating the flow, right? So it's kind of, we have an equilibrium of the forces. So in a fluid at rest, the stresses correspond so let's think about this. What do these stresses, the surface stresses, the contact forces in a fluid at rest corresponds to? Imagine you have these stresses and you have a fluid at rest. So what are the contact forces that kind of are imposed to the surface of these fluid particle here? Yeah, it is pressure. So the stresses correspond to pressure in a fluid at rest, which acts normal to surfaces, right? It acts on the surfaces, but it's normal to the surfaces, any surface that you get. Okay? So in a fluid at rest, tangential stresses are not possible. So are not possible for a fluid at rest or at equilibrium, since otherwise the fluid would just move or flow. So let's see why. So say you have a fluid particle and then you impose a tangential stress to this. So you have this tangential stress. So what happens to this fluid particle? It just keeps moving. So first it becomes this was actually the definition of a fluid. It will keep moving until you exert the force. So first it becomes like this, and then it becomes like this. So it just keeps moving, and it deforms continuously under a tangential stress. So these tangential stresses are not possible for a fluid that is at rest. This is only possible if we have a fluid that is moving. So we can have this continuous deformation. So what does this mean and what does this entail? This means that the stress tensor sigma ij for a fluid at rest is gonna be so in the diagonal of this matrix, if you remember, we have the normal forces. So the normal forces are just in the diagonal of this matrix. Sigma 1, 1, sigma 2, 2. So you can see it here. This is the normal force, sigma 1, 1, sigma 2, 2, sigma 3, 3, right? So they are all in the diagonal of this matrix. And we know that the pressure forces are always normal to the surface, right? So for example, if you have, let's say, a fluid particle, then the pressure forces are gonna be to the normal, the pressure stress or the pressure forces, which are gonna be the normal stresses, are gonna be always normal to the surface to keep this in equilibrium, right? So we will have also other pressure forces equal to in the other side to keep this fluid in equilibrium. Okay. So what would be the stress tensor? First of all, the pressure, what is the sign of this? So the sign of this, the n vector is always outward and the pressure stress is toward inside the control volume. So the sign of it is going to be minus P. And then for the other tangential stresses, as we said, like tau 1, sigma 1, 2, sigma 1, 2, sigma 1, 3, sigma 2, 1, all the tangential stresses like this, as we showed here, they do not exist for a fluid at rest, for a fluid that is at equilibrium, because it causes them to move. So those pressures, those stresses in a fluid at rest should be 0. And then only the diagonal part of that, which we have the normal stresses, should equal to the pressure. So this will be our stress tensor in a fluid at rest. Okay, so sigma ij for a fluid at rest is just equals to the sigma ii. Ii means in the diagonal part, right? So I, again, you can change I and j from 1, 2, 3, and j from 1, 2, 3, right? So this is like a sum. So this is like sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3, right? So this is the whole stresses. So I put this in the parentheses. This equals to minus P times delta ij. And let me say what is delta ij if you don't know. So delta ij is just a mathematical operator. Is just 0 if I does not equal to j, and it will be 1 if I equals to j. It's called the Kronecker delta. So here it's going to be minus p if I equals to 1 is if I equals to j. So if you have 1, 1, it will be 1. If you have 2, 2, j equals to 2 and I equals to 2, it will be also 1. And if I equals to 3 and j equals to 3, this delta will be also 1, so we will have p here. Otherwise, it will be always 0. So for example, what we can say here, say we want to say sigma 1, 3 here. This equals to minus p delta 1, 3. And based on this, because I does not equal to j, delta is going to be 0, so p times 0, this becomes 0. Also, sigma, let's say I want to calculate sigma 2, 2. So it's going to be minus p delta 2, 2. Based on this, I equals to j, so delta ij is going to be 1. So p times 1, so this will be minus p, which is here. And the first one, sigma 1, 3, here. Okay, so this is just a simplification to write these kind of stresses. Okay. Now, let's calculate stresses in a fluid at motion. Let me write this. Should be like that. Let me. In a fluid at motion. Okay. So for out of equilibrium, out of equilibrium systems, that is fluid motions, we have, so the sigma ij is going to be sigma, the stress tensor sigma ij will be minus p delta ij, this is for the fluid at rest, plus some additional stresses. We need some additional tangential stresses plus tau ij. Okay, so we can write it as this. So this is stress in a fluid at rest, and this is additional stress due to fluid motion and deformation of fluid particles. Okay. So this is now how we are going to decompose the stress into a stress in fluid at rest and a fluid at motion. And one thing that we know from the first few lectures, that in a Newtonian fluid, tau, or the shear stress, is linearly related to the local instantaneous velocity gradient. What does this mean? For example, if you remember from the first few lectures, we mentioned that for a Newtonian fluid, let me see if I can write exactly the same thing that we had. So say here we have y, and here we have u, which is in the x direction. Okay, so now I want to write what is, say, Tyx the stresses that is kind of acting in this direction in a flow, Tyx, for a flow that is has a velocity like this. So this we know based on the Newtonian formula, that is going to be mu partial u partial y, right? So this is for a Newtonian fluid, and this is what we know from in the past. Okay, so now we are going to use this, and then in the next session I am going to use this to drive a formula for the tau ij, which are the additional stresses due to fluid motion, and then finalize the stress tensor and put it back into the original momentum equation to drive the momentum equation for viscous incompressible fluids, which is actually gonna be the Navier-Stokes equation. Okay, so let me shortly review what we learned today and in this lecture. So we want to drive the Navier-Stokes equation. So we started with the continuity equations that we had before, and also the partial differential form of the momentum equation for inviscid fluids. So we don't have any viscosity here. And now we now want to consider it for a Newtonian viscous fluid for a general form. So we write it in terms of stress, surface contact forces, and also body forces. So in terms of surface contact forces, we can write a general linear momentum equation as this, where sigma is the stress tensor, and this is for the surface forces, and this is for body forces. Okay, and then we discuss what is Cauchy stress tensor. So we just show the stress tensor, all the stress elements, and talked about a little bit of its properties, like it's a second order symmetric tensor. And then we derive the stresses in a fluid at rest, which is basically is just going to be pressure, because we cannot have tangential stresses in a fluid that is at rest. So this is the relation for the stress tensor in a fluid at rest, or this one too. And then we started to derive these stresses in a fluid at motion, so we can decompose it into two components: one for stress in a fluid at rest, and one additional stresses due to fluid motion, which we are going to derive in the next lecture based on this linearly related relation between the shear stresses and velocity gradients. Thank you very much, everyone.